Okay, section 5.3 is on conditional probability and the multiplication rule. And we're going to look at conditional probability first. And the symbol for conditional probability is that it's the probability of B given A. That's how we write it, so it's B/A. And so what this means is it's the probability of B given that A has already occurred. So you might know something about your sample, like for example, if you're looking at something where you're separating it according to males and females, you might know that the person selected is a female. So you could find the probability of some characteristic given that it's a female, that you already know you have a female. And you'll find in the textbook a formula for the conditional probability, but to be honest with you, I never ever use that formula because these can just usually, or always in our case, be calculated based on just figuring it out. You don't have to use a formula. So let's look at an example. So it says, the following table presents the results of a survey in which 400 college students were asked whether they listened to music while studying. And so we have the results right here. So first of all, this is what we call a contingency table, and you'll see those a lot when you're dealing with conditional probability. And so you always want to have totals. Sometimes they'll give you the totals for the columns and the rows. Sometimes you have to put them in yourself. In this case, we're going to have to put them in ourselves. So we're going to have some total columns and a total row. And the whole thing should add up to 400 because they tell us that's how many students were surveyed. So the total number of males would be 121 plus 78. That's 199. And the total number of females would be 147 plus 54. That's 201. Notice how those add to 400. Then the total number that listen to music while they're studying is 121 plus 147. That's 268. And the total number that do not listen to music while studying is 78 plus 54. That's 132. And again, notice that 268 plus 132 add to 400. So we're going to need those totals as we do these problems. Okay. And so now we're going to answer some questions about this. So first of all, it says one person is selected at random. That's important. Take note of that because when we get to the multiplication rule, that's when we're going to look at when more than one person is selected. But right now, it's still one person selected at random, and we want to find some different probabilities. So the first one says, is a male who does not listen to music while studying. Now, this is not a conditional probability because we're not given any condition. We could have done this problem in the last section. So we're looking for the probability of a male who does not listen. Okay, so we're taking it out of the total group. We're not given anything to narrow it down. So the denominator is still going to be 400. And then we just need to look at the table and see how many are males who do not listen. And that's going to be this number right here because it's where the males and the do not listen overlap. So that's 78 out of 400. Now you could go ahead and convert that to a decimal. I'm not going to as I do these examples. The important thing is being able to find the numbers. You would just divide and get a decimal there. Okay, so this is one that we could have done in the last section. Now let's take a look at number 2. Number 2 says find the probability that the person is a female given that they listen to music while studying. So writing that out, we're looking for the probability of a female given that they listen. Okay, so whatever that given that condition is, that comes second in your symbolic notation of this. It comes after the slash. And that's going to give you your bottom number. So the ones who listen, that's how we're going to get our denominator. Because we know that the person is somebody who listens. So what that means is we're narrowing it down so that we're only looking at this column. Because we know going into it that it's somebody who listens. So to calculate it, our denominator is going to be the total number who listen. So that's going to be 268. And then the numerator, well, we're looking for the number of females. Well, we're only looking at that highlighted column, so the number of females are 147. And again, you could divide that and make it a decimal. So whatever that given that condition is, that's going to narrow down. It's either going to narrow it down to one column or narrow it down to one row. And then you're going to just look at that column or row. And the total will be your bottom number, and then you get the numerator according to what they're asking for. Okay, so let's switch it around this time. Let's look at number 3. Number 3 says find the probability that the person listens to music while studying, given that it's a female. So notice I'm switching the order from number 2. So in this case, we're looking for the probability that they listen, given that it's a female. So remember, whatever condition you're given, that's what's going to narrow it down for you. So this time we're given that it's a female. So we're going to narrow it down to this row only because we know that it's a female. So my bottom number is going to be 201. That's how many females there are. And then for the top number, well, we're looking for the amount that listen. So the ones that are in the listen column are 147. So notice with these two questions, what changed was the denominator. The numerator was still the same. And that's because what's changing is what you're given. And number 2, we're given that they listen to music, so we need the total that listen to music. And number 3, we're given that it's female, so we need the total of females. Okay, let's do one more. Let's find the probability that the person does not listen to music while studying, given that it is a male. It is a male. So we want the probability that they do not listen, given that it's male. So we need to first decide, whenever we have a given condition, you've got to first decide what you're narrowing it down to. So we're given that it's a male, so we're looking only at the males. So we're just looking at this row right here. So the bottom number is going to be 199, and then out of those, how many do not listen? 78. So it's going to be 78 out of 199. And so notice doing that, we did not use any sort of formula. We were able to just figure it out by looking at the contingency table. And that will be the case with any of the problems that you do with conditional probability. Okay, we'll come back to this when we get to the textbook examples. The next thing I want to look at are independent events. So we talked in the last section about mutually exclusive events. Remember, those are ones that cannot happen at the same time. Independent events are ones where if one occurs, it doesn't affect whether the other one occurs or not. The most classic example of that I usually use is gender of children in a family. A family can have 5 girls. You know, they have 5 babies and they're all girls. And then they want to go for that boy. They want that 6th child. Surely it'll be a boy. Well, unfortunately, the events are independent. So the fact that they had 5 girls already has no bearing on what's going to happen with the gender of this baby. It's still a 50-50 chance. So they're independent. So the definition of this is the occurrence of one does not affect the probability that the other event occurs. So let's look at some examples. So what we have to do here is they're going to give us two events, and it says that assume that a student is chosen at random from a class. Determine whether the events A and B are independent, mutually exclusive, or neither. Okay, so for number 28, it says the student is on the basketball team is event A, and event B is the student is more than 6 feet tall. And we're going to go with the most obvious answer here. You could probably make an argument for any of them, but we're just going to use, keep things simple. So, first of all, let's talk about independent. Well, to be independent, it would have to be the case that the student being on the basketball team and the student being more than 6 feet tall have nothing to do with each other. And usually that's not the case. Usually basketball players are more than 6 feet tall. So I would say they're not independent. And then mutually exclusive would be that they can't happen at the same time. Well, again, they can definitely happen at the same time. A student can be on the basketball team and be more than 6 feet tall at the same time. So for this first one, it's neither. Okay, let's take a look at number 30. Number 30 says event A is the student is a woman, and event B is the student belongs to a fraternity. And if you're not familiar with this word, a fraternity or a frat is a club in college for males, and then sororities are for girls. So the student is a woman and the student belongs to a fraternity. Those would be mutually exclusive. In most situations, that cannot happen at the same time, to be a female and belong to a fraternity. So they're mutually exclusive. Okay, the next thing I want to talk about is the multiplication rule. Now the multiplication rule, I would say the most important thing to remember about the multiplication rule is it's used when selecting two or more items. So as soon as you see that you're selecting more than one, you want to think about the multiplication rule. And what the multiplication rule says is that the probability of A and B, so these occurring at the same time, A and B, is equal to the probability of A times the probability of B. And what you're going to do right here is you need to assume A has occurred. So when you calculate these probabilities, you always, when you calculate the second one, you always assume that the first one has happened. Now, if the events A and B are independent, then it's not going to matter that A has already occurred. And when we look at some examples, I'll show you where that comes into play. So let's go back to this example that we talked about earlier with the males and the females and whether they listen to music while they study or not. And I went ahead and wrote the totals in. So we're using that same contingency table we had earlier. So let's start with number 1. It says, suppose two people are selected at random, and notice that it says with replacement. You'll see that a lot with probability when you're selecting more than one. And what that means is they select the first person, and then when they go to select the second person, they put that first person back into the pool. So theoretically, the same person could be chosen twice. So you're doing it with replacement. You see it a lot with like a deck of cards. If you select a card with replacement, then you're going to select one, take note of what it is, and then put it back before you select the second one. So these are going to be independent events because the fact that the first one occurs isn't going to affect the probability that the second one occurs because you're putting that person back into the pool of things. Okay, so let's do these. So we want to find the probability that they both listen to music. So we're looking for the probability of listens and listens. And just remember that when you're doing selecting more than one, you're going to multiply. This is where the multiplication rule comes in. So this is going to be the probability that someone listens times the probability that someone listens. Okay, well, the probability that somebody listens, there are a total of 268. We're not given any conditions, so we're doing everything out of the grand total. So there's 268 that listen out of 400. Times, now we selected that one person who listens, but we put them back into the pool. So the probability that the second person listens is also 268 out of 400. And so if we calculate this, we're going to have 268 out of 400 times 268 out of 400. And we get 0.4489. Now, let's go down to number 2. I'll do part B in a minute, but let's go down to number 2 and rework it. Notice that it's the same question. Suppose two people are selected at random, but this time it's without replacement. These are not going to be independent because the fact that whatever you select first is going to affect the probability of what you select second. So this time we're not putting that first person back into the pool. So we want the same question, find the probability that they both listen to music. So again, we have the probability of listens and listens. And we're still going to multiply because we're selecting more than one. So it's going to be the probability that the first listens times the probability that the second listens. Well, the probability that the first listens is going to be the same as it was in number 1. There's 268 that listen out of 400 times, now this time we're not putting that first person back in. So our bottom number is going to be 399 because we have one less person and we assume the first event happened. So we assume that our first selection was somebody who listens. So now we only have 267 left that listen to music. And you'll multiply that just like I did the last one. You're going to just type in 268 divided by 400 times 267 divided by 399. And this time we get 0.4483. So slightly less probability of that happening if we do it without replacement. So notice how the fact that the first event happened, that changed the probability of the second event. That's why when you do it without replacement, they're not independent. Okay, let's take a look at part B for each of these. I think I'm going to have to erase this so I have enough room. Just remember, without replacement is not independent. Okay, so for this one, we want to find the probability that the first is a female who listens and the second is a female who does not listen. Okay, so this probability, so we want, I'm going to use some abbreviations here, female who listens and female who does not listen. I don't know. Let's do it like that. So, and this one is with replacement. So that means that my bottom number on both of these, when I multiply, is going to be 400 because we're putting that first person back in once we select. So females that listen, I want to find that category. Females that listen, 147. out of 400. And then the second one is females who do not listen. Females who do not listen is 54. And so when we multiply that, we're going to have 147 divided by 400 times 54 divided by 400. And hopefully you have your calculator with you as you're watching these videos, so you can do all the calculations with me and make sure you're doing them right. This time we get 0.0496. Now let's rework it this time as not independent, as dependent events when we do it without replacement. So again, we're finding the probability of a female who listens, and the second person is a female who does not listen. Okay, so again, the first one's still going to be the same. There are 147 out of 400 who listen. Now, for the second person, well, we have one less person to choose from, so 399. But notice with this one, because the second category is different from the first was females who listen, the second is females who do not listen, we assume the first happened. So we assume that we chose a female that listened. So the females that do not listen, there is still 54 of them, but it's out of 399 now. And so when you multiply that, 147 divided by 400 times 54 divided by 399, we get 0.0497. Almost the same number, but not quite. You can see it's slightly more likely to happen without replacement. Okay, let's look at another question using the same data. Excuse me. Suppose 5 people are selected at random without replacement. Find the probability that they all listen to music while studying. Well, I wanted to do this one to show you that you don't have to limit it to 2. Here we're selecting 5 people, so we're going to have 5 products. We're going to multiply 5 numbers together. And so we want to find the probability that all 5 listen. And notice it's without replacement. You always want to take note of that. So for the first number, let's see, the probability of listening when they select the first person is 268 out of 400. And then we're just going to multiply each of them. So for the second person, we assume the first happened, so there's only going to be 267 out of 399. And then for the next one, there's going to be 266 out of 398. And then for the fourth person, it's going to be 265 out of 397. And then finally, for the fifth person, it's going to be 264 out of 396. And so notice the bottom number will always be going down when you do it without replacement. In this case, the top number is also going down because we're keeping them all in the same category. We're all looking at listening to music while studying. And when you type this in your calculator, I'm going to show you this one, but you can just type it all in at once. Just type each fraction with division. So we're going to start off with 268 divided by 400. And then the next one was 267 divided by 399. Excuse me. The next one was 266 divided by 398. And then 265 divided by 397. And then 264 divided by 396. And so we get 0.1333. So that would be the probability that they all listen to music when you select 5. Okay, let's do one more example with this problem, and then we'll look at some textbook examples. Okay, so this time we're going to suppose 3 people are selected at random with replacement. So notice this time we're putting each person back before we select the next person. Find the probability that at least one does not listen to music while studying. Okay, so we want the probability that at least one does not listen to music. Okay. Well, one way to do this is to do it directly. And so what we would have to do is figure out, when you're selecting 3 people, all the different ways that you could get at least one that does not listen to music. So just to kind of give you a little overview of that, you could have, I'm going to let L stand for listen and D stand for does not listen. Okay, so if we do it directly, if at least one does not listen, we have lots of different ways that could happen. You could have does not listen, does not listen, does not listen, where they all 3 do not listen. Or you could have does not listen and listen, listen. Or listen, does not listen and listen. Or listen, listen and does not listen. Or you could have does not, and listens. Or does not, listens, and does not. And I'm just going to say etc. So these would be, you could just list all of those and then calculate each one individually and add them together. We don't want to do that. That would be crazy. In this problem, it would be doable. There'd be a lot of combinations, but imagine if you had something even larger than this. So we don't want to do it that way. So when you see this at least one, it is always, always easier to use the complement. And so the opposite of having at least one that does not listen is having none that do not listen. I'm getting all sorts of negatives going on here. So what you can do whenever you have at least one is you can rewrite this as 1 minus the probability of the opposite. So change the at least one to none. So 1 minus the probability that none do not listen. Now that is really bad English. So another way to say that would be 1 minus the probability that they all listen. Because if there are none that do not listen to music while they study, then they all listen to music while they study. And using this complement allows us to just calculate one probability instead of all these different ones that we were looking at over here. We can just calculate the probability that they all listen and subtract it from 1. So this will be 1 minus, well, the probability that the first person listens to music while they study. Let's go back to the table. I think it's 268 out of 400, but let me make sure. Yeah. So the ones that listen are 268 out of 400. So the probability that the first person selected listens is 268 out of 400. And then we're going to multiply just like before because we're selecting more than one. Then the probability that the second person listens, well, we were doing this one with replacement. So that's going to be 268 out of 400. And then the probability that the third person listens is 268 out of 400. And then we're going to subtract that from 1. So another way to write this, since all 3 of these numbers are exactly the same, since we did it with replacement, you can write this as 268 out of 400 cubed. And it's 1 minus that. And you can just type that right into your calculator. So we'll do 1 minus the quantity 268 divided by 400 cubed. And to get cubed, you'll see this, I'm going to make it red when I click it. It's right above the divide, and that's how you get things up to an exponent. It's called the caret button, and it's going to be cubed, and then enter. And so that probability is 0.6992. That's the same number you would have gotten if you had figured out every single combination where you can have at least one that does not listen, and then calculate each of those and add them together. But it's much easier to use the complement. So whenever you see at least one, I want you to think of 1 minus the probability of the opposite. So I'll write that down here. If you have the probability of at least one, whatever, fill in the blank there, that's going to be always equal to 1 minus the probability that none do whatever the blank is. So like if you were selecting marbles from a jar, the probability of getting at least one red would be 1 minus the probability of getting no red. Excuse me. Sorry about this cough. Okay. Let's look at some examples from the book. So on page 299, we're going to start with number 36. So it says an unfair coin has a probability of 0.4 of landing heads. So the probability of heads is equal to 0.4. That's why it's an unfair coin, because it should be 0.5. The coin is tossed 4 times. What is the probability that it lands heads at least once? Okay, well, first of all, I don't know if I'm going to need it or not, but what would the probability of tails be if the probability of heads is 0.4? Well, these are the only 2 events, so we can use the rule of the complement here. The probability of tails would be 1 minus 0.4, or 0.6. And we're tossing it 4 times. And we want the probability of at least 1 heads. Okay, well, like we just said earlier, up here boxed in red, it's always easier to do the complement with at least 1. So I'm going to rewrite this as 1 minus the probability. Well, the opposite of getting at least 1 head is getting no heads. And what would no heads look like? Well, it would look like, we're tossing it 4 times, so it would look like tails, 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 tails. And tossing a coin, those should be considered independent events. It's just like the gender of a baby. You know, you can toss a coin and get heads the first time. That has no bearing on what you're going to get when you toss the coin the second time. So they're independent. So each of the probabilities will be the same. So the probability of getting a tails the first time is 0.6. And we're doing it more than once, so we're going to multiply. So tails the second time is 0.6, tails the third time is 0.6, and tails the fourth time is 0.6. So another way to write this would be 1 minus 0.6 to the fourth. And so that will be the probability of getting at least 1 heads. So let's do that calculation. So we have 1 minus 0.6 raised to the 4th power. And so that's 0.8704. So again, just remember that whenever you see this at least 1, you can change that to none and so use the complement, 1 minus. Don't forget the 1 minus. Okay, let's look at another one. Okay, number 38. Charles has 6 songs on a playlist. Each song is by a different artist. The artists are Usher, Kesha, Lady Gaga, Eminem, and Black Eyed Peas and Ludacris. He programs his player to play the songs in a random order without repetition. That's going to be important. That's like the same thing as saying without replacement. What is the probability that the first song is by Lady Gaga and the second song is by Eminem? Okay, so we want the probability that the first is Lady Gaga and the second is Eminem. Well, we know that when you're selecting more than one, and we're looking at two songs, you multiply. So we're going to take the probability that the first is Lady Gaga times the probability that the second is Eminem. Okay, so what is the probability that the first one is Lady Gaga? Well, she has one song out of the 6 songs on his playlist, so that would be 1 out of 6. Now, they're being played without repetition, so it's not going to choose from the Lady Gaga song when it goes to choose the second song. So there's only 5 songs to choose from, but only one of them is from Eminem. So it's going to be 1/6 times 1/5, which is 1/30th, or if you want to convert that to a decimal, you'll do 1 divided by 30, or you could do 1/6 times 1/5, same thing, and we get 0.0333. So that would be the probability that that exact order would happen for the first 2 songs. Okay. Let's take a look at number 40. Number 40, they give us a table again. So the following table displays the 100 senators of the 113th U.S. Congress on January 3rd, 2013, viewed by political party affiliation and gender. Okay. So notice they already give us the totals. If they didn't, we would have to do that, but they gave them to us. So let's answer some of these questions. So for for this question, it says a senator is selected at random from this group. So notice that we're only selecting one. So I'm not going to be using the multiplication rule on these questions. Okay, so first of all, what is the probability that the senator is a woman? So we just want the probability of woman. So this is a question we could have done in the last section, or even the section before that. There's a total of 20 females out of 100. And I'm just going to leave the fractions on these. But, well, now we can divide. It's going to be 0.2. Excuse me. Okay. Now for the part B, what is the probability that the senator is a Republican? So we want the probability of Republican. Well, again, the total is 46. There are 46 Republicans this year in the Congress, back in 2013, and that's out of 100. So that would be 0.46. So with questions A and B, those are just standard probability questions. You're just taking the total amount out of, or the amount out of the total amount. Okay, same with part C, actually. What is the probability that the senator is a Republican and a woman? So we're still only selecting one. So even though I have an and in there, I'm not multiplying. We're just looking for the probability of getting a Republican female if we select one senator. So the number, so it's still out of 100. And the number of Republican females is 4. So that would be 4 out of 100, or 0.04. Okay, now starting with part D, we've got some conditional probability. And it can be worded differently. Notice here it says, given that the senator is a woman, what is the probability that she is a Republican? That could also be worded as, what is the probability of a Republican given it is a female? were a woman or whatever. So the given condition can be written in the beginning of the sentence or the end of the sentence, but it's still the given condition. That's still going to be your denominator. So I recommend with these conditional probabilities, first write it symbolically. So we're trying to find the probability that she's a Republican. That's what we're looking for, given that it's a woman. So that's what we're given. And so whatever you're given is going to give you your denominator. Remember, we talked about that. So the denominator comes from the given condition. And so we're given that it's a woman, so we're only going to be looking at the female column. So the bottom number is going to be 20. And then how many of those are Republicans? That's 4. So it'll be 4 divided by 20, which is 0.2. So if you know that it's a woman, there's a 20% probability she's a Republican. Okay, let's look at part E. They're flipping it around now. Given that the senator is a Republican, what is the probability that the senator is a woman? So this time our given condition is Republican. So we want the probability of woman given she is a Republican. So we know that it's a Republican, so we're going to be looking at this row. And so our bottom number is going to be 46. And then how many of those are women? 4. So it's 4 out of 46, which is 0.0870. If we round to 4 decimal places. Okay, let's look at another question. This one is on quality control. It says a population of 600 semiconductor wafers contains wafers from 3 lots. The wafers are, there they go again, are categorized by lot and by whether they conform to a thickness specification with results shown in the following table. A wafer is chosen at random from the population. So again, notice that we're just selecting one. That's always important to keep in mind. If you're just selecting one, you are not going to use the multiplication rule. And they don't give us totals on this one, so I'm going to add to my table here with totals. I'm going to have to kind of write over. I didn't leave myself enough room. Okay. So let's put in the totals. So lot A, we have a total of 88 plus 12, that's 100. B, we have 165 plus 35, that's 200. And C, we have 260 plus 40, that's 300. So notice there was a grand total of 600. And then conforming, 88 plus 165 plus 260, that'll be 513. And non-conforming, 12 plus 35 plus 40, that's 87. And notice that those two total 600 as well. So if you can read between the lines here, we want to answer this question. What is the probability that the wafer is from lot A? Okay, so I'm not given any conditions or anything. I'm just looking for the probability that a randomly selected wafer came from lot A. So the bottom number is the grand total because we're not given any conditions. So it'll be 600. And then how many came from lot A? Well, 100 came from lot A. So it's 100 divided by 600, or 1/6. Or if you want to convert that to a decimal, it's 0.1667. That's usually what I'll have you do on the exams, is convert them to decimals. Okay, what is the probability that the wafer is conforming? Well, again, we're not given any conditions, so our bottom number is going to be 600. And then how many are conforming out of the 600? Well, that's our total for conforming. That's 513. So that decimal will be 513 divided by 600, which is 0.855. And it divides, you don't have to round. That goes in evenly. Okay, let's look at part C. Part C says, what is the probability that the wafer is from lot A and is conforming? So we want to find the probability of getting something from A that is conforming. Well, again, we're not given any condition. It will literally say the words, given that. So I know my bottom number is still the grand total of 600. And then how many are from lot A and conforming at the same time? That's this number right here, 88. So that will be 88 out of 600, which is 0.1467. Okay, now we're going to do some given that's. So for part D, given that the wafer is from lot A, what is the probability that it is conforming? So let's put that symbolically. The given that comes second. So we want the probability that it's conforming given that it comes from lot A. And whatever comes second in your symbolic notation, that's what you're going to narrow it down to. So we're only going to look at lot A. So we are just looking at this row right here. So the bottom number is going to be 100. And then how many of those are conforming? 88. So that will be 88 out of 100, or 0.88. Okay, let's look at part E. Part E says, given that the wafer is conforming, what is the probability that it's from lot A? So this time we're given that it's conforming, and we want to find the probability that it comes from lot A. So we're given that it's conforming, so that's going to narrow it down to the conforming column. So we're just looking at this column. So the bottom number is going to be 513, and how many of those are from lot A? 88 of them. So it's going to be 88 out of 513. And that is equal to 0.1715. Okay, and then finally for part F, let E1 be the event that the wafer comes from lot A, and let E2 be the event that the wafer is conforming. Are E1 and E2 independent? And explain. Okay, well, E1 means that it comes from lot A. E2 is that it's conforming. Okay, well, if they are independent, then the fact that the first one occurs is going to have no bearing on the probability of the second one. So if they're independent, the probability of E1 is going to have to equal the probability of E1 given that E2 occurred. If they're independent, those two are going to be the same because the occurrence of E2 wouldn't affect the probability of E1. So the probability of E1 is the probability that it comes from lot A. And I believe we answered that in part A. We did. It was 0.1667. And then this is the probability of E1. And then the probability of E1 given E2 would be the probability that it came from lot A given that it's conforming. Well, we found that in part E. That was 0.1715. And so since these two are not the same, they're not equal, that tells me that they're not independent. Because if they were independent, then it wouldn't matter that we had already that it was conforming when we select A, but it did matter. It changed the probability when we knew it was conforming, so they're not independent. Okay, I think I have one last example. Maybe not, maybe a couple more. Let's take a look at number 44. 44 says the Bureau of Labor and Statistics reported that 64.5 million women and 74.6 million men were employed. Of the women, 25.8 million had management jobs, and of the men, 25.0 million had management jobs. An employed person is chosen at random. So again, notice we're just selecting one. There's not going to be any multiplication rule going on here. What is the probability that the person is a female? So we want the probability of female. Well, we don't have a grand total, so let's summarize what they give us. So we know that 64.5, it's all in millions, so I'm going to leave that off. There are 64.5 women in the workforce and 74.6 men in the workforce. So there are, let's get the total there, 64.5 plus 74.6 gives us 139.1 total. And then we know that 25.8 women are in management. And 25.0 men are in management. And so of those, there's a total, I don't know if I'm going to need this number, but let's get it just in case, of 50.8 total in management. Okay, so it's just helpful to kind of summarize things. I always do that when I'm doing these types of problems. So the probability that if we select one person at random of it being a female, well, there are 64.5 females out of a total of 139.1. So we're not differentiating between whether they're in management or not. So 64.5 divided by 139.1 gives us 0.4637. Okay, what is the probability that the person has a management job? So I do need that total for management. So the probability that they have a management job, well, there are 50.3 total, or no, that's an 8. 50.8 total in management, and that's out of 139.1. So notice how my denominator is the grand total for these. That's because we're not given any condition. We're just taking it out of the whole group. And so when I convert this one to a decimal, 50.8 divided by 139.1, we get 0.3652. Okay, then what is the probability that the person is female and has a management job? So we want the probability of a female and they're in management. Okay, so how many females are in management? That's 25.8. We're not given any conditions, so it's still out of the grand total, 139.1. It doesn't say given that. They just have two characteristics. So 25.8 out of 139.1 gives us 0.1855. Okay, now we're going to look at some given that conditions. Given that the person is a female, what is the probability that she has a management job? So we want the probability that it's management given that it's a female. So notice how we always write it symbolically first. Okay, and remember the second one, that total is going to be your denominator. So how many females did we have? We had a total of 64.5 females. Because we know that it's a female. And how many of those were in management? Well, it was 25.8 that were in management. So 25.8 divided by 64.5 is 0.4. So if we know that it's a female, there's a 40% chance she's in management. Okay, now for part E, it says, given that the person has a management job, what is the probability that the person is a female? So we're going to flip it around. What's the probability of a female given that they're in management? So this time the bottom number is going to be the total that are in management, which I believe was 50.8. Yeah. And then of those, how many are female? Well, 25.8. So 50.8 are in management. And then 25.8 were the number of females that were in management. So 25.8 divided by 50.8 is 0.5079. Okay. I think I have one last example. Yeah, number 56 here. Actually, I have two more examples. I'm trying to get my... Just close your eyes for a second if this bothers you. I apologize. Sometimes it gets weird when I scroll. Okay, so for 56, car warranty. The probability that a certain make of car will need repairs in the first 6 months is 0.3. A dealer sells 5 such cars. What is the probability that at least one of them will require repairs in the first 6 months? So first of all, notice that we're selecting more than one. We're selecting 5. So we're going to use the multiplication rule. Also notice that we're talking about at least one. So we're probably going to use the rule of complements as well. So they tell us that the probability that it needs repairs in the first 6 months is 0.3. So that means that the probability that it does not need repairs in the first 6 months is the opposite of that. That would be 0.7. They need to add to 1. And we want to find the probability that at least one of the 5 will require repairs. So we want the probability of at least one repairs. Well, with at least one, it's going to be easier to flip it around and use the complement. So we're going to switch it to 1 minus the probability and change your at least one to none or no. So that's going to be 1 minus the probability of no repairs for all 5 cars. Well, so that will be 1 minus. Now the probability that the first car doesn't need repairs is 0.7. The probability that the second car doesn't need repairs is 0.7, and so on. And there are 5 such cars. So I can just go ahead and put that to the 5th power. So we're going to take 1 minus 0.7 to the 5th. And that gives us 0.8319. So that would be the probability that at least one of those 5 cars that the dealer sold needs repairs within the first 6 months. Okay. And by the way, in the next chapter, we're going to learn another way to do a problem like this where you just have 2 outcomes. It either needs repairs or it doesn't need repairs. We refer to that as a binomial experiment, and we'll learn another way to do that. Okay, let's look at one more example. For number 58, it says the technology consulting company Data Genetics suggests that 17.8% of all 4-digit personal identification numbers or PIN codes have a repeating digits format such as 2525. Assuming this to be true, if the PIN codes of 6 people are selected at random, what is the probability that at least one of them will have repeating digits? Okay, so the probability of repeating digits is 0.178, because it's 17.8%. And so then the opposite of that, the probability of no repeating digits, is going to be 1 minus that. So 1 minus 0.178 is 0.822. And so we're going to select 6 people. So that tells me I'm going to be using the multiplication rule. What is the probability that at least one of them will have repeating digits? So we want the probability of at least one repeating digits. Well, again, we're going to change the at least one to none or no and subtract it from 1. So it's going to be 1 minus the probability of no repeating digits for all 5 or all 6 of the people selected. So that's going to be 1 minus. Now the probability of having no repeating digits is 0.822. And you're going to multiply that 6 times for each of the 6 people. So that'll be raised to the 6th power. And so we're going to take 1 minus 0.822 to the 6th power. And so that probability is 0.6915. So if you randomly select 6 people, there's about a 69% chance that at least one of them has repeating digits in their PIN number. Okay, and that finishes up section 5.3.